at some point mentoring some of us during these 10 years since my scholarship, my postdoc position there in UCSD. We have Victor, Pedro, Gustavo, and myself. So today, Professor Krstic is not talking about extreme thinking, but since Tamer provoked us about this section, I don't know. I have a story about the logo of our event. It's like some waves that represent the frequency of the extreme seeking, trying to find the quadratic function, the optimum of the quadratic function, which would be the representation, of some of the maximum of the sugar loaf. So it's a joke, internal joke, because we're trying to find a logo using AI, and this was the end point when we decided, okay, this one is good for the conference. So, Professor Krstic, do you need some help?
No, I don't think so. I just wonder if I did some damage to this. I don't know what this is. No,
this is for just to capture the sound.
Uh-huh.
Okay.
Okay. And you guys are recording this?
Yes.
Where is this going?
We're going to put this on the website, and possibly we're going to share in the Brazilian Society of Automatics website. So this is part of our objective, because we're going to collect this and share with all the students that we have in this big society.
So we better be in control of our jokes and humor, right?
Oh, you
this
can
is
do
going
this.
Public?
No, you can do this.
Well, you think I can do, but I feel differently about this. So it's great to be here. Thank you for organizing this. I hope everybody got the drift of the title of this workshop. Control in Rio, like rock in Rio, yes. Right? That's the idea. Okay, so it's wonderful to be here, and it really is caps off many years of collaboration. And of course, I'm not going to talk about extremum seeking in a place that has taken the lead in extremum seeking away from me. I have some other topic instead. It's good to see the Colombian duo come here, because they converge to extremum seeking, one from the PD end of things, another one from hybrid end of things, and there's some incredible innovation resulting from that as well. And I've got a little bit from both of you, coincidentally, in these slides, not by plan, because I wasn't expecting you. So I observed that a portion of my slides were presented at Professor Bashar's recent a workshop celebrating his major life milestone. And if I'm not misremembering, a portion of your slides, Tamer, were presented at my 60th, if I'm not misremembering. So what a nice symmetry there. By the way, it just occurred to me, the trip to Rome, that's in January, right?
That's in December, end of December.
I see. So it's somewhat uncorrelated to the milestone, or it is just shifted, adjusted to the availability. Right. I got it finally. All right. So this is the topic that I want to talk about, and you might be wondering, why is he? He's not a geometric mechanics guy. Why talk about these ancient questions now? I should tell you why, because there is logic to speaking about this somewhat antiquated subject, which remained unsolved, and since 1983, Brockett's condition till now. There is a reason why I'm talking about it. The reason is very mundane. I got a grant from the Office of Naval Research on some problems in managing vehicle traffic in certain environments. and I spent 2 years working on designing excellent safety filters that avoid collision avoidance. But I couldn't find good nominal controllers that actually perform good transitions from point A to point B, namely the basic fundamental parking problems, and I just could not. This was so unsatisfying that we can develop excellent veneer, but at the core, the content is poor. So I rolled up my sleeves, and the result of that are these results. I'm not talking about pursuit evasion. That is what I spoke about in Urbana in September. I'm staying at the level of a single vehicle. So what you will see in these slides is first the development of globally stabilizing feedback laws, which in addition to being globally stabilizing, they're all of the LgV or the gradient form, which means that they happen to have optimality properties in a meaningful way. And as a bonus of optimality, of inverse optimality, they also have infinite robustness to gain uncertainties, infinite gain margins, even greater than the common gain margins from 1/2 up to infinity. These have gain margins from 0 to infinity because the system, the non-holonomic mobile robots are driftless systems, unlike the general x dot equals ax plus b systems. I will also talk about inverse optimality in the presence of adaptive control. This should interest everybody who has interest in reinforcement learning, which is a form of adaptive optimal control. I'm going to be talking here about optimal adaptive control. Adaptive optimal control is optimal once time reaches infinity. Optimal adaptive control is optimal over the entire infinite horizon and extremely hard to achieve, but achievable in these systems. And finally, the bit that should interest, again, my Colombian friends is that I'll show some very recent results on achieving stabilization, not just asymptotically, but in finite and in fact in fixed time, using some of the tools that they've pioneered or advanced. So let's start with the model. Everybody knows this model. The unicycle model, 3 states, the position xy, the heading theta, 2 inputs, the longitudinal velocity v appearing in these 2 equations, and the angular velocity or steering omega. If that's the model from which you start, you just can't get very far. It turns out that the right model, and this has been observed in robotics as a footnote in 1995 and never paid attention to almost at all in the control literature. That's not the right model for control design. The right model is not the Cartesian representation, but the polar representation. I'm not talking about something tricky. I'm talking about something very, very basic. Why would you be married to the Cartesian representation if the polar representation gives you advantages? So I'm changing the representation from xy into rho, which is the distance from the parking destination, and delta, which is the angular component of the position relative to the parking target. And now I get this system. Now that system you're unlikely to have seen before. But that is a system that is just God sent for controlling for parking, solving parking problems. It's a strange system, though. There is a division by the state rho, which is the distance from the target, and there is a singularity at the parking target position. That singularity, rather than being a headache, will be God sent for the design. It'll make the design possible and meaningful. So, you know that Brockett said that you can't even achieve stabilization locally Well, I'm going to be talking about stabilization and even globally. I will get to the disclaimer how to reconcile Brockett with what I'm talking about. I'll get to it in 15 minutes, maybe 10 to 15 minutes. So by global stabilization, I mean for all initial positions and for all initial headings. And to make that possible, I'm going to use the control fully. I'm going to use the steering. I'm going to use the driving, both forward and in reverse. That's kind of pretty important. The ability to shift in reverse as we do in parking is pretty important. So let me start from this model. When you look at this model for a bit, you see one distance-like state and two angle-like states. So it's reasonable to think about, okay, let me focus on controlling the distance separately from controlling the two angles. And when you look at the distance equation, the longitudinal velocity, the driving speed, appears in a linear fashion in it. And you think about it heuristically for a little bit, for a few minutes, and you arrive at the conclusion, well, why not just take the velocity in this way, so that in closed loop rho dot is proportional to minus rho. In other words, you slow down as you approach the destination. Now, when you take this feedback, you're also including the cosine of the line of sight angle gamma. I'm sorry, I did not emphasize what gamma is. Gamma is the line of sight angle of the vehicle relative to the target position. You're introducing this cosine, and for a moment you think, well, that's a mess. But it's not a mess, it totally makes sense. It means that you are going to go forwards or in reverse depending on the line of sight angle. If I'm oriented this way and I want to go to Tiago's position, I'm kind of faced somewhat away from him. I'm going to go into reverse. I'm not going to go forward. That's kind of like the roundabout way to go to the target. So it makes sense. So I'm finished with the design of the forward velocity feedback. It's this. And now I'm left with two state equations. Let me just dispose of the first one. This is the system. It's a second order system. You take a look at it. It's nonlinear. It's not in the conventional strict feedback form. It's not globally feedback linearizable. It's a bit of a strange but elegant looking system. And it's perfect. You can't do trivial things with it, but it's only two states. You can do interesting, non-trivial things with it. And basically, all of the three major tool bags for nonlinear control designs apply. You can do a passivity-based design, you can do a forwarding-based design, and you can take the strongest of the hammers, backstepping, and you can use that design. The outcomes are different, the feedback laws are different, and I will walk you briefly through that. Now, first, before I show designs, let's talk about the state space. The state space is actually the designer's choice. It's up to the designer to decide whether they're going to think of these angles as living on the interval from minus pi to pi or on the whole real line. This is somewhat of an aesthetical choice. It has some practical consequences, But it is a choice. If you take the angles to both be in R on the full real line, you get a global design. If you take one of the angles, or both, to be on the interval from minus pi to pi, you cannot get a global result. You can get an almost global result. For people who have that aesthetical preference, not to be repetitive, not to have the angle wind, the answer is that if that is your aesthetical preference, then your state space is not the plane, nor is it the cylinder. If you want both angles to be from minus pi to pi, your state space is the torus. And these designs cannot, there's a topological impossibility of a global stabilization of the torus. There's going to be an exclusion of a zero measure set of initial conditions. This red circle and this blue circle will be excluded from the region of attraction of this desired equilibrium. This desired equilibrium corresponds to being at the target positionally and being at the target heading, namely parked in the right direction. So this is just a preliminary observation about the state space. If you take the torus and slice it and unwrap it and place it on the plane, the Lyapunov stabilization that is almost global is in fact the construction of a control Lyapunov function that has level sets like this. Because those two circles are excluded and those two circles represent actually the edges of this square, you see how the level sets are getting denser, and you have global stabilization on this square as reflected by these Lyapunov level sets. All right, let me now show you some controllers. I said 3 design methods: passivity, forwarding, and backstepping. I will show you an example from each of these 3 families of designs. Now, in each of the families of designs, you can pick the state space to be the R2, or to be the torus, or to be one of the 2 cylinders. You have many, many possibilities. So I can just give you some examples. Let me start with an example of a passivity-based design on the torus. There is no time to explain why how these designs are derived. I just have to bang these designs, and if you're from the nonlinear control world, they may begin to make sense to you. If you're not, then not even that is possible, but we will get still something out of this. So when it comes to passivity, the passivity-based control approaches are based on physical energy functions. And the physical energy function, the potential energy in the angle space on the torus, happens to be the sum of these squared tangents. The tangents exclude the point plus minus pi from the state space. So the tangents are exactly what you want. So that is the physical potential energy. At the end of the design, which I'm skipping, which is actually pages almost of Lyapunov construction and analysis, you arrive at the feedback law for the angular velocity, which is given by this expression, which depends only on the angles. It doesn't depend on the distance. The steering is independent of the distance. It depends only on the angles. Now, you can stare at this, and the only thing that jumps at you is that, there's a whole bunch of trigonometric functions there. And yes, that's, I think, the only thing that one can discern out of this, and it's not shocking, it's not nonsensical. The system has trigonometric functions. The Lyapunov function has trigonometric functions, and so does the feedback law. And the feedback law gets more and more aggressive as you approach those circles that are excluded from the region of attraction. This is the price. Aggressive control is the price that you pay for your aesthetical preference of having the state space be a circle or the torus, the cross product of the circles, rather than R2. Now, I called this a Lyapunov function, but that Lyapunov function really is not one that does the full job. That Lyapunov function is non-strict. Namely, u dot is not negative definite, but only negative semi-definite. So the actual Lyapunov function, the strict Lyapunov function, and you will see why we want those, is given by this expression, which there's nothing simple about it. Something that is relatively simple is this summing up of the tangents and squaring of that. But then U, the original potential energy, needs to be included with a sufficiently high power, namely with a sufficiently high emphasis. And then this Lyapunov function is strict. This V dot is negative definite under that control. All right, let me speed up now a little bit. The second of the three control families is forwarding. Forwarding takes the state in which the control does not appear and applies a very intricately cooked up transformation to that state. So the state where on which the angular velocity does not directly act is delta, the angular component of the position. And there is a transformation. This transformation looks simple, but it's arrived at, if you know forwarding, in a very complicated manner through some explicit solution of some closed loop system, the integration, the explicit integration of that closed loop system, the various things. And then at the end, what pops out for the unicycle is something beautifully simple as the sign. The feedback law on a cylinder, namely taking one of the angles to be on a circle and the other one to be on the whole real line, happens to be this feedback law. And again, it's hard to make sense out of this in any detail, but it is nearly globally stabilizing, and that is so with respect to this control Lyapunov function. This, the time derivative of this is strictly negative definite. And finally, the backstepping design is in some way kind of dual. So the state that is directly affected by omega, the steering, is what is being transformed relative to the other state. The feedback law that results from introducing a transformation like that is this expression. Again, a whole bunch of signs and so on, but not everything is trigonometric. There are parts that are linear because we're not on a torus, now we're on a cylinder. And the control Lyapunov function, which is strict, is given by this sum of the squared tangent and the squared transform state z. Now, what does one get as a theoretical result? What is the theorem? The theorem is global asymptotic stabilization in the particular norm on the respective state space, which if the state space is R2 for the angles, it's R2. If the state space is the torus, it gets a little more complicated. I'm dropping those details. There's nothing complex about that. The result is global on the respective state space in the sense of having a class KL estimate on the solution. All right. If I stop here, this should really confuse you because it looks like it contradicts Brockett. Brockett says that this is impossible. But there is no contradiction. If you go back to the coordinates in which Brockett establishes the impossibility, namely the Cartesian coordinates, you get an estimate, a KL looking estimate that looks like this. And I'm highlighting in blue a term that is added to the norm in the Cartesian coordinates. It's some number. It doesn't matter what it is. This arctangent 2 is unimportant. It is a non-zero number. So this is not an asymptotic stability result in the Cartesian coordinates. In polar it is. In the Cartesian it's not. What is it? After some brainstorming and discussion about terminology and concepts in stability with Iason Karafillis, we settled on the following name. There is no stability here. There is attractivity and there is boundedness. So this is global uniform, not Lyapunov, but Lagrange asymptotic stability. A property that was really never sought in our field, but this is the best one can achieve for this problem. Had Brockett thought that that's a possibility, maybe within a few years this would have been achieved. But Brockett set what would be without the blue term as a possibility, and the unachievability of that was the result of the succeeding efforts. By the way, if you're Hungarian, to you this is pronounced as goulash. So that's the dish I serve you today. It's pretty spicy because it's uncommon. So now let's make sense out of this. What is going on? These parking trajectories are so nice and beautiful. There's nothing weird about this. They look stable. They look stable, but there is no stability. Look at this parallel parking maneuver from here to here. If you simply go like this, your angle will have undergone a transition of nearly pi. No matter how close you start. This is not stability. This is just Lagrange stability, just boundedness plus convergence. If you look at these more conventional parallel parking maneuvers, the excursion of the angle is smaller than pi. If you look at a possible parking maneuver, the excursion of the angle is 2 pi. So, no, there's nothing. This looks like stability, but it is not stability because stability is impossible in the Cartesian coordinates according to Brockett. So now, if you have a preference for achieving asymptotic stability, Brockett does not prohibit asymptotic stabilization. He just says it's impossible by static state feedback. He doesn't say it's impossible by time-varying feedback. So, time-varying feedback laws started with Courant, and that got refined. Well, they got started by Claude Samson, but not for the unicycle. Then Courant, and finally the first fully satisfactory design was by Pomé in 1992. Well, if you don't like this form of parking because conceptually it is not stable, then be my guest and go ahead and park like this, because this is stable. This is stable. You see? You get the closer you, the smaller the distance that you go away, the less of an excursion you have both in x and y and in theta. But practically, we never want to do this. Okay? So I'll take this over this. Now, you saw me present a KL estimate of, several slides back. This KL estimate, this KL estimate, global, asymptotic, and it's actually local exponential as well. But now we're in an era where prescribed time by time varying feedback and fixed time by time invariant but non-smooth feedback is very hot and exciting, because we can go beyond asymptotic and even exponential stability speed. We can get stabilization in arbitrary time. So of course, I've been involved with that, and I have to look into that problem. So this is a result on which I'm on the same wavelength with Nicholas Espitia, who was the first to develop a really reasonable and usable prescribed time feedback stabilizing law for PDs. Now, this is not a PD, it's a nonlinear system. And the solution to prescribed time stabilization for the unicycle is to take the feedback laws developed for asymptotic stabilization and simply multiply them by 1 plus the tangent squared, where tangent squared is a growing gain. These quantities go to 0 faster than this one does, and the stabilization in prescribed time is achieved. The specific statement is this statement, a KL estimate like the one that you saw before, but instead of time, there is time that blows up as time as the actual time approaches the prescribed time capital T. And in addition, the input signals are not only bounded, but they also converge to 0 as you approach the terminal time. That's the time varying version, and you can see it in action here in polar coordinates. The distance, the angles, everything goes to 0 and lands infinitely smoothly at terminal time to the destination. The more interesting part is looking at the control inputs. You see how both control inputs are not only bounded, but they also go to 0 and do so with infinitely many derivatives going to 0 as well. Okay, now immediately, we have to ask the question, but can finite time and fixed time stabilization be achieved without these gains that are taken to infinity? Can be achieved with non-smooth means? And the answer is, yeah, that is doable as well. And instead of gains that go to 0 as functions of time, instead of gains that go to infinity as functions of time, it's these gains that are non-smooth that enable the fixed time stabilization outcome. And the fixed time stabilization result is formulated with this class KL estimate, which goes to 0 no later than time capital T, and it's identically 0 from the time capital T onward. And that's supposed to resonate with Jorge Poveda, who has pioneered extremum seeking in prescribed time with me and with Professor Bashar. Now, which one is better? I will not declare the winner here. You can stare at these trajectories using PT or using time varying or non-smooth approaches. I claim that by adjusting different parameters, they can both work comparably well. There is no winner here in terms of performance, nor in terms of the control effort. That is my experience so far with this. When it comes, there's a difference in noise robustness. Neither one Neither one is super robust, but time varying is sketchier in that domain. All right, let me now return to Lyapunov stabilization and inverse optimal control. So now I'm going to be designing a completely different family of stabilizing controllers, which are not just stabilizing but also optimal. And I need to make it clear what are my control Lyapunov functions. I've shown you control Lyapunov functions for only 2 of the 3 states, namely for the angles delta and gamma. But rho is also a state. The distance from the target is also a state. So I haven't shown you completely Lyapunov functions, and they can be constructed in a number of ways. The simplest one being simply the sum of the distance squared and of these angle CLFs. But you can do more interesting things. You can involve the logs. You can involve these exponentials. This one's my favorite, and I will get to it one more time. And it's positive definite. Not maybe entirely obvious, but it is positive definite. Here is something that I've never seen observed, a very, very fundamental, crucial property I haven't seen observed in the CLF theory since Sontag's result since his universal control in 1989. If you don't have drift, if you don't have f of x in the nonlinear system, and if you manage to design a CLF, which for a driftless system is very hard, as you've seen, when the number of inputs is smaller than the number of state components, then with any positive gain, the LgV feedback is globally asymptotically stabilizing, and LgV, the norm of LgV, is positive definite. That is definitely not the case if you have drift. So thanks to this special property of driftless systems, it happens so that you can take the LgV relative to both of these 2 inputs to the unicycle, the longitudinal and the angular velocity, and you can multiply them with any positive constant, epsilon 1 squared or epsilon 2 squared. And for any of these gains, no matter how large, but more interestingly, no matter how small, the feedback will be stabilizing, but more relevantly now for the inverse optimal discussion, the feedback will also be optimal for any of these coefficients. How can all controllers be optimal? Well, each of these controllers is optimal for the respective gain which enters the cost function. If epsilon is very small, you're penalizing these inputs very heavily. If epsilon is very large, you're penalizing them lightly. And the state, the LgV contributions of the state respectively. So I've just introduced for you a whole separate family of controllers. The original ones were stabilizing. These are stabilizing and optimal. Am I getting something different? And am I getting something better? On the left are the non-inverse optimal controllers. And if you look at their trajectories, I would say you would not object to parking in this manner. This is exactly how you would probably park in most situations for most of these initial positions and orientations to this. So this looks good. When I look at these, to me, these look natural as well. Which one is better? Again, I want to avoid saying what's better because these things, each one of them has at least 3 different gains. You can shape these. The point is not which one is better. The point is that there is an expanded set of transient shaping possibilities, and for this one on the right, you can never be wrong because they have an infinite gain margin. The control never acts in the wrong direction in the control theoretic sense. I'm running out of time. Let me tell you something briefly. If a controller has an infinite gain margin, can it be saturated? Can it be saturated to an arbitrarily low level? And the answer is yes, those things as well. Is it optimal? Once it's saturated, even that, it is optimal. So you actually can establish the stabilization and the optimality for the saturated versions of the LgV controllers, where phi, for example, can be the saturation function. This is harder to read on a quick read, but that's what it means, what I just said in words. So, if you saturate the LgV terms, the trajectories in the plane, they don't change at all. What changes is the speed with which you travel along these trajectories. That's fascinating. You can see the difference in the steering. The steering that you get with LgV controllers is those curves, and with saturated LgV controllers is those curves. Which one do you prefer? Well, I prefer this because, you know, common sense. You can't steer arbitrarily fast. The Dubin's vehicle is fundamentally steering rate limited. So I prefer this because it acts as hard as it can at its full steering capacity until it's done. And it actually happens to be done in finite time. All right, let me now evolve this optimality story a little further. So you heard from Tamer about some very advanced forms of games. Let me now consider a game within the setting of parking. So still a single vehicle, still the same model as before, but now I'm introducing a disturbance that is matched with the angular velocity. This is an angular velocity disturbance. Physically, what might disturb the angular velocity? Well, wheel misalignment, uneven tire pressure, worn steering rack bushings. Oh my God! When you think about all of these repairs, you don't want to think about going to your mechanic. But all of these things are disturbances to steering. So here's the theorem. Take the same feedback law that I've given you before in the absence of a disturbance. In the presence of a disturbance, this feedback law ensures integral input to state stability, and in addition, it ensures inverse optimality relative to this game formulation, minimax game formulation. This feedback law minimizes the maximum maximized over the disturbance of this cost function, which includes positive penalties on the longitudinal and angular velocities, and a negative quadratic penalty on these angular velocity disturbances. For a penalty on the disturbance that is in this range. Finally, let me tell you the part that I think is that I really like, maybe the most of all of this. So now let me come back to what I was saying, adaptive optimal control versus optimal adaptive control. So I'm going to show you a result in optimal adaptive control that is optimal over the entire horizon. The inspiration actually comes from Tom Ayer's work in the very early 90s with two PhD students at the time, one working on H-infinity based adaptive estimation or identification, and the other one working on adaptive control, Didinsky and Pan. So suppose now that the input authority, the driving authority, B1, is not 1. It's in fact unknown. I just don't know. I'm not designing a controller. I don't know how powerful the engine will be. It's highly uncertain. And I also don't know how responsive the vehicle will be to steering. And I want to use adaptive control. I'm robust to those uncertainties. But some greed for performance or for saving on the control effort is driving me to go even beyond robustness and to employ adaptation. So here's the answer to this. Instead of those epsilons that you saw me use along with the LgV controllers, I'm going to introduce adaptive gains, and these adapted gains, zeta 1 hat and zeta 2 hat, they're exponentiated for a purely mathematical reason, because if I exponentiate a quantity, the result will always be positive. That's, to make things mathematically neat and fully global, I exponentiate my updates. And how do I update these gains? So I update these gains with these update laws, where the update gains mu1 and mu2 are positive, and where this normalization function n is a differentiable class k infinity function. So these are the update laws. LgV is squared, n is k infinity, n prime is positive, the exponentials are positive. These are update laws that take the gains zeta 1 hat and zeta 2 hat only in the positive, in the growing direction. Okay, so I'm never backing off on the gains. I'm increasing the gains up to what is necessary. Just to be clear on that. I'm not saying that this is smart. I'm just telling you what it is. My non-adaptive result has infinite gain robustness, so it shouldn't be surprising that I start with a small gain and take gain in an upward direction as high as necessary based on the transits. The update law contained the LG1V and LG2V, and I never really mentioned what these things are. So this is what they are. They're some non-trivial expressions that are based on what G is in the unicycle model. So now LgV contains V. So let me remind you what the V's are in the three designs. In the passivity-based design, the Lyapunov function V is given by this line. In the forwarding-based design, it's given by these expressions. And in the backstepping design, by these two expressions. I'm just removing any mystery, just to remind you what all that goes into implementing these feedback laws. So now, what can I prove for these adaptive controllers? I can prove two things: stability, not surprising, and optimality of those adaptive controls over the entire horizon. Let me first dispose of the stability. So stability holds in the following manner. The Lyapunov function, which contains which upper bounds the norm of the Planck state, is upper bounded by the inverse of this normalization function acting on the adaptive Lyapunov function. What is the adaptive Lyapunov function? The adaptive Lyapunov function is this expression, which is positive definite in V and in the parameter estimation error zeta tilde, which is defined here as a difference between the updated gain zeta hat and a certain constant that depends on the unknown input coefficient or control authority B. The function psi of zeta tilde is an interesting exponential of exponentials functions, as it happens to be the case, which is never smaller than 1. The whole thing here, the whole blue expression, is positive definite, though not radially unbounded in zeta tilde. What happens with the gains? Do the gains drift? In the absence of disturbances, there is an explicit upper bound on how far the gains will get, depending on the initial conditions. I hope, as an editor, for this level of honesty in adaptive control papers, explicit bounds as to how big the things that don't converge, or even things that do converge, may get. And that's how big these may get. And finally, regulation. This is not a KL estimate because we have adaptation, but it is the convergence part of the KL property that I showed. Finally, my second to last slide, and this is the one that I'm most pleased about. So this adaptive controller is optimal. It minimizes this cost functional. So now we need to take a look at this cost functional and decide, make a decision. Is it meaningful? Does it make sense? Do we like this or not? Well, this cost functional within the brackets is something you've seen before, except that there are now elements of the adaptive gains that appear in here, but those things are always bounded and positive. What is new is the presence of psi of zeta tilde, which is a penalty on the adaptation rate. I must remind you what that is because it's complicated. It's this expression. It depends on the gain estimation error. So this adaptive controller is a minimizer not only of what's happening to the plant, but it's also a minimizer of the learning error across the entire horizon. This is why I insist optimal adaptive rather than adaptive optimal. And finally, since this is an optimal control problem, what is the optimal value function? It's that complicated expression on the previous page in which I emphasize its dependence on the parameter error. This expression, VA, the adaptive Lyapunov function. So, final slide. How does it work? This is the transient of the norm of the whole system. I'm not showing you trajectories. They all look like what you've seen before. They'll all look good. Nothing. I don't want to repeat that. How is the control effort? Well, this is why I went through this exercise. Red is the non-adaptive controller. This is the gain robust controller. You see that the red is always more aggressive than these adaptive gains because they start with very, very tender levels of gains. When my state is large, I use low gain. Then as my state gets closer, as I approach the target, the gains get pumped up because of the price paid during the transient. So the control never gets very, very large because it didn't start with a high gain. Its gain got large only when the state got small. And with that, I'll stop here, and if there's any time for a question, I'll be happy to try to answer.
Thank you.